So if we have the standard model, which is just L0, the usual standard model, then we know as part of the way of constructing it that we wrote down all the operators with dimension less than or equal to 4. And we also know that it was normalizable in a traditional sense. So now let's talk about the standard model corrections, i.e. terms in the standard model from an effective field theory point of view that are operators we can write down, like L1. So L1 will look like, I can write it in the following way, which is kind of a convenient thing to do. Pull out the scale lambda nu, leave over some dimensionless constant. So I'll just use some scale lambda nu for all the operators that I consider, and I'll just allow for differences between the various scales that the operators could have to be taken up by dimensionless constants. And O5 here is a dimension 5 operator. So the dimension of C is 0. And we'll, in a power counting notation, we say C is of order 1. That means that we don't count any powers of lambda nu associated to C. What we've done here is we've made the power explicit by just writing it in. So that's often convenient, just in the same way it was convenient to make the S's explicit in that argument. Now we're just building up the theory, writing down operators, making the lambda nu's, which are our power counting parameter, very explicit. Now, the statement that in the standard model it was normalizable in the traditional sense, I told you that what that meant is that nothing in lambda 0, nothing in Lagrangian 0 really tells us about lambda nu. So we're free to take it as big as we want. There's no constraint on it from our leading order Lagrangian. And in particular, we can take it much bigger than things like the top mass or the W mass. And we can make these corrections as small as we want. So L1 is therefore really, we can think of it as really giving some small corrections, and we can adjust how small they are by just dialing up the scale of lambda nu. All right, so let's get down to business and actually talk about what this Lagrangian is. So our notation is that we index the Lagrangian in a series. This is our sum over n that we talked about last time. And our power counting is that we associate this guy here with no powers of lambda nu, this guy here with 1 inverse power, this guy here with 2 inverse power, etc. And we want to think about using this for some p, which you could say is of order m top squared, some scale that's much less than the lambda nu. Could be larger than m top, could be 10 TeV, whatever we decide, but it's just in order for me to write something on the board, let me write m top. OK, so how do we construct L1 and L2? What do we assume? Well, one thing we assume, or our free to assume, and is a reasonable assumption, is that there are not going to be any Lorentz invariants or gauge invariant violating terms. Okay, so we can maintain these as symmetries of our theory. So we assume that they're unbroken. So that means when we write down these L1 and L2, or generically each Li, that we're going to have to do it by writing down operators that are gauge invariant. Even though they're higher dimension, we still have to satisfy gauge invariance of the standard model and Lorentz invariance. Okay, so that's going to restrict what we can do. We also construct Li from the same degrees of freedom that we have in L0. So we know what fields to use. Okay, so that's important. It means that once you've got the leading order effective field theory, you know where to go for the higher order terms. You're just using the same fields. I'll also make the assumption that the Higgs vacuum expectation value is going to stay to be the value in L0. And that, so the way that the gauge group is broken by the Higgs vacuum expectation value is spontaneously broken. We're not going to mess with that. And built into this idea that we do this is that there's no new particles that are produced at P. If there was a new particle produced at P, then it would have to have a mass that would allow us to produce it. And that would mean that it doesn't have a mass up at this lambda nu scale, and we'd have to include it in our effective Lagrangian. So by taking this point of view, we're assuming that there's no new particles that are produced at the scale P, only at lambda nu. And effectively, we've integrated out, if you want to use that language, although we're doing this from the bottom up. If you want to have a top-down language, you'd say we integrated out the particles at the scale lambda nu. OK, so that's our logic. So then we just start seeing what we can write down. And for the dimension 5, it's actually very restrictive. Gauge symmetry is very restrictive for dimension 5. And there's basically only one operator. So we won't stop at dimension 5. We'll go up to dimension 6. So at dimension 5, it turns out that once you satisfy the gauge symmetry, the unique term that you can write down looks like this. And my notation is that this guy is our left-handed leptons with a charge conjugation operator. And these guys are doublets, so the Higgs doublet is a doublet like that, and the left-handed leptons, neutrino, and electron is a doublet like that. So these are doublets. And figuring out how to contract the doublet indices, but I have to satisfy the U1 hypercharge gauge invariance. This has no color, so that's automatically satisfied. And then I have to satisfy the SU2, and I've done that by the way that the indices are contracted. One thing I didn't write down in this operator is flavor indices. So if you were to add flavor indices, you could do a bit more, but that's just in some sense, that's a pretty simple generalization. So we'll still count it as one, even though we could think about having more flavors and contracting things with more flavors, and that wouldn't, of course, affect arguments made on gauge symmetry alone. So in all my counting today, I'll be agnostic about flavor matrices. So when I say only, that proviso is hidden there. OK. So this guy's kind of interesting from a phenomenological point of view, because if you replace the Higgs field by its vacuum expectation value, which means getting rid of H plus and taking H0 to be a constant, which is V, then that gives a Majorana mass term. So the observed left-handed neutrino would get a term in its Lagrangian that looks like, after we do that, it looks like that, and that's a Majorana mass term. Where this m nu is a parameter that shows up, but it's built out of the parameters that were in this thing. So once I replace these by vevs and go through the various factors, we get something like that. So just the fact that we know that the observed neutrino masses are less than, say, 0.5 eV tells us something about the scale. So if this is small, if C5 is of order 1, I told you we know what V is. It's 246 GeV. That tells us something about lambda nu. But it's big. So we could try to think up some reasons why the C5 maybe has some suppression in it and make the scale a little bit smaller. But if C5 is order 1, then we get a very large lambda nu scale. I'll give you a problem on your problem set to explore this in a little more detail. I should also note that the Majorana mass term, having two neutrinos like this, violates lepton number, which was a global symmetry of the standard model. At least classically. There's dimension 6 operators that so this guy violates lepton numbers. You can also write down dimension 6 operators that violate baryon number. And I'm going to leave that also as a problem set problem. So you'll figure out what those operators are. So example 3. If I conserve lepton number and baryon number, which are things that are, if they're broken, that's obviously having a big impact, and there's obviously strong constraints on that. So you could ask then, if you go to dimension 6, and we conserve those things, because they are highly constrained, how many operators there are left over, and there's 59. So L2, we can count exactly how many operators there are. Some coefficients, and some operators that are dimension 6. And if I want to make a lambda nu explicit, I put a lambda nu squared in there.
So 59 sounds like a big number, but big is always relative. So if you think about 59 relative to, for example, how many soft SUSY breaking parameters you have in the minimal supersymmetric standard model, which is greater than 100, then the number 59 does not sound so bad.
Also, you should remember that if you're going to do some phenomenology with this L2,
that many of the 59 are not going to contribute.
if you look at a particular process, only some small subset of them will contribute. And there's many, many, many observables in the standard model with all the different particles.
So 59, once you start dividing it up into
camps that contribute to different observables, is not such a large number. Or at least it's not an unmanageable number, and people do phenomenology with this. So for any observable, only a manageable number contribute. And I should also say that if you have a top-down perspective, where you have a new physics theory that you've constructed that has a scale lambda nu in it, then from this point of view, what that theory predicts is a particular pattern for the C's. Hopefully, if it has less parameters
than 59,
then you get some patterns, you get connections between the C's. Okay, so if you have some new physics model that has
the numbers of parameters in it are less than 59,
then you get connections between these C's, and you could think that if you use this Lagrangian constrain the C's, that you could test for generically for classes of new physics theories that are ruled in or ruled out, because they have to, if you match onto these C's from those theories, obey whatever constraints you would derive from this logic. Of course, that assumes that the new physics particles are at a high scale, so we can make this expansion. Okay. So questions about that? Yeah.
What about your assumption that you don't have like new degree freedom is like sharing in the high order? Like,
yeah.
If you want them to be like comparable or measurable for high order, wouldn't I expect that like they have to be like at higher energy? And why is it at a higher energy that no new degree of freedom?
So it's not to say that at higher energy the no new degrees of freedom would show up if I really probe those energies directly. But what I'm doing is I'm saying that I'm probing the physics at small energy. And the way that a high energy degrees of freedom would show up is by a contribution to one of these operators. So say I added in some new particle at 10 TeV, mass of 10 TeV. If I expand in momentum over that mass, then what will happen is you'll get an operator like this O6, where that particle is removed because I expanded it, it got removed. And its mass will be exactly in this denominator. It'll show up here as lambda nu. So think about it as like lambda nu squared could just be the propagator. If I had it 1 over p squared minus some massive, I don't know, some gluino, right? And then I start expanding this. The first term where I drop the momentum is just that, and that could be exactly this lambda nu squared. So the new physics particles don't show up in OI6. What they affect is the prefactor. So you don't need to add new physics particles in order to construct the operators. You're just building those operators out of the standard model degrees of freedom.
So you're still working in P, which is much smaller.
Yes, yes, then the lambda nu. Is there another question? Okay, so I've been assuming some familiarity with the standard model here, and I've posted also, as I said last time, my lecture notes on quantum field theory 3, and there's some review reading there. Some of this is unfamiliar to you, is discussing VEVs and things like that. Okay, so what kind of operators can we have at dimension 6?
I'm not going to list all 59.
Obviously, but I'll list a few of them. So we could take an operator that's the following, built out of gluon field strengths. So making it Lorentz invariant, contracting up the indices, and contracting up color indices. Contracting up color indices with an FABC. That's an operator that's dimension 6, because the G's are dimension 2. And that's one of the 80. You could also do something with fermions.
Sorry, what are the indices
In here. Whoops. Yeah, what happened? All right, there we go. Thanks. So here's something with a lepton doublet and a quark doublet. We already introduced the notation for LL, and QL is similar, but just for up and down. So that's each fermion dimension 3/2, so 4 of them is dimension 6. There's something called magnetic operators. So there's lots of different things you can do with 4 fermions. I've only given you one example. And I've posted the reference for the paper that lists all 80. So you can look at it if you want to look at the complete list. So we could do something where we have leptons, a Higgs field, as well as a field strength for the SU2. So this is in the SU2. And these are all gauge invariant, as you can convince yourself by looking at the standard model gauge transformations of these operators. And so if I write something like this, where this is a doublet and this is a doublet, and I don't write the doublet contraction, then I'm just contracting those indices. These two here contribute to the muon magnetic moment, anomalous moment. So they contribute to G minus 2. G minus 2 of the muon, which is something that we've measured to very high precision, has what you would call, sometimes you would call standard model contributions, which people usually mean is the contributions in our notation from L0, and then plus some contributions from these higher dimension operators, whatever coefficients these operators have. And again, I would replace the Higgs field here by a VEV. I know I have their dimension 6, so there's lambda nu squared downstairs. One factor of dimension is made up by the VEV, and then the next scale that comes in is the mass of the muon. So this is the generic size of those contributions. And again, if you take into account experimentally how well we've measured this, it puts a pretty strong, or at least it puts a constraint on lambda nu. Actually, it's probably stronger than this number. Some number greater than 100 TeV, maybe it's even 1,000 TeV.
The standard model contribution is almost W.
Yeah. So the standard model contribution makes up all the digits we've measured. And then there's some digits where there's some uncertainty. We have and you can constrain based on the experimental uncertainty how big this possible contribution could be. And there's 2.5 kind of deviations from the standard model in this observable, so you can make up for them with a dimension, with an operator like that. But I never really pay attention to things that are less than 4 sigma personally. Though sometimes it's interesting to get excited about 3 sigma. No, I'm not. Yeah. So there's also flavor on top of that. That's right.
So flavor is actually highly constrained, and you could put in some assumptions about flavor, and then you'd get to this 59. Okay, so for the remaining 55.
See the reference I posted. So this paper actually wasn't the first to try to enumerate these operators. As you can imagine, this would be a pretty standard thing to do. But it was the first to get 80. And the reason that they got 80 where other people got more is because they used the equations of motion to simplify the operators. So let me let me phrase that as, is there a caveat? So when they did their counting of the operators, they took the equations of motion from L0 and they used that to simplify L1. So they worked out the standard model equations of motion at tree level, and then they applied those equations of motion to reduce the form of the operators down to 80. So that got rid of a lot of operators for them that other people had considered as part of the counting in the past.
In fact, a complete use of the equations of motion can be kind of tricky. The classical analysis of Buchmeiler and Weiler stood actually for 25 years with these 80 operators, until in 2010, Grodkowski, Igrinsky, Misiak, and Rosiak showed that the true count was actually 59.
So for example, so you get some idea, if I have a covariant derivative acting on a right-handed electron, then the equation of motion in the standard model relates that to Yukawa couplings. Here I'm writing the flavor indices and the left-handed doublet, Higgs field and the left-handed doublet. So this would be like a mass term if I put in the VAV. So that's like the analog, if I write it in terms of spinors, of P slash U for the right-handed electron is mu, but just written as an equation of motion. So they're using things like this to get rid of covariant derivatives acting on the right-handed electron and just replace it by an operator that a priori doesn't look like it's the equivalent, which is H dagger L. Now, if you are stuck at tree level, is just to think that you apply this in a way that is valid when you look at lowest order, at the operators at lowest order. Then it's pretty obvious, actually, that this is OK. Because the external lines, if the lines that are coming out of your operator are always external lines, then when you look at the Feynman rule for those lines, you're putting them on shell. So for example, let's think that we had an operator that is not part of their list. So H dagger H, E right, ID slash E right. You won't find that as one of the ones that's listed
in those papers.
You could think about the Feynman rule for that. So there's two Higgs particles, say, and two right-handed electrons. And if I just take the derivative out of here, then I get a P slash. And if I use P slash is mu, then I get just U bar U. And so this is, of course, connecting us to the left-handed doublet, the left-handed guy. So this operator, in that sense of thinking about using the equation of motion, which are connecting left and right fields, putting them together in the standard model, is connecting this operator to the one that would just have H dagger L, and you could just immediately get the right result just by starting with that operator, and that's the logic that they used. So you don't have to write this down because it's redundant. You get the same result from writing this down. So that seems fairly straightforward at tree level and at lowest order, where all the fields are external. But I actually claim that it's true regardless of what I do. Whether I have loops, whether I have propagators, it's OK. We can do this. And that seems a lot less trivial. But it is true.
This is actually really cool.
Because it's a pretty powerful thing to do if we are allowed to use these equations of motion to simplify the form of the higher dimension operators in our effective field theory. It certainly helps us to reduce the number of operators.